Testing, testing, testing. Okay, so for this question, we have to find the correct answer, because I was looking through it and I found out that it's not like the right answer. Like the right answer is not included in the choices. So let's see what we can do. All right. To determine how well a bicycle wheel is lubricated, the mechanic in the repair shop gives it a spin. All right. So that means that there has to be some sort of initial speed, right? Some initial angular speed, more specifically, since we're talking about rotational motion. So here's our wheel, and then we're going to give it some initial speed, some initial angular speed, omega 0. Now the mechanic measures the time t before it stops, right, and counts the number of revolutions n. So if there are 100 revolutions per minute, right, so if t equals 1 minute and n equals 100, that means that we have 100, okay, RPM, or 100 revolutions per minute. Okay, so what's the magnitude of the angular acceleration in radians per second squared? Now, it would make more sense if we simply use the first kinematics equation per se, right, for angular rotation, for rotational kinematics, right? We know that the final angular velocity equals to the initial angular velocity plus alpha t, right? So we're trying to look for alpha. We know that the final velocity, final angular velocity will be 0, since it will stop at some point, right? We know t, we know omega 0, okay? So alpha will be negative omega 0 divided by the time. So let's see. We know that 1 revolution, equals 2 pi radians, right? So it takes 2 pi radians to make 1 revolution, right? To go around once, or 360 degrees. It's the same. Okay, so if we do some unit analysis, right? If we do some unit analysis to find the angular velocity, the initial angular velocity, we do 100 revolutions, right, in 1 minute. Okay, 100 revolutions in 1 minute, and that's basically what 1 minute is 60 seconds. So that's going to be our speed, right? That's going to be our angular velocity, and we want that in terms of radians per second. So multiply by 2 pi radians per 1 revolution. That goes away, right? So we have that the initial angular velocity is 200 pi radians over 60 seconds. All right. So we go back to this equation, right? Alpha, the angular acceleration, or deceleration as we call it, because we're decelerating, right? Negative, right, of the initial angular velocity, which is 200 pi radians over 60 seconds. And that is going to, occur in a period of, right, 1 minute. So over 60 seconds. or 200 pi radians. 200 pi radians, okay, divided by 60 seconds squared. Okay, so if I plug that into our, the calculator, decimals, 200 pi divided by 60 squared, okay, is going to give me, okay, since we have negative in front, we have negative 0.17, about 0.17 radians per second squared, okay, and this to me is it's a convincing answer. So this is the actual, okay, angular deceleration. Over here they say it's 0.35, but that's not the case, okay. 0.35, okay, it's twice as much as 0.17, but that doesn't mean that, of course, that doesn't mean that it's going to be the right answer. According to this, okay, method, using kinematics equation, we can easily get the angular deceleration, then this is the right answer. So sometimes there might be wrong answer choices on the test, and well, that's all right. I mean, there's no issue with that. You'll probably get your points if that were to happen. All right, last question. This is an interesting question. Okay, so an Atwood machine similar to an elevator with a counterweight is initially at rest. On one side is a mass of 2 kilograms, and on the other side is a mass of 1 kilogram. So we have something like this. Okay, one mass going this way, okay, and that's 2 kilos, and the other mass this way, and it's just 1 kilo. All right, so we know that this is going to move in this direction, right? The angular acceleration will be in this direction, so that will be the positive direction, and this will be the negative direction. Now let's see what happens next. A massless core that passes over a pulley connects the two weights, right? So that's what's happening. The pulley has a mass of 4 kilograms, a radius of 20 centimeters. So this is 2 kilos. The radius, okay, R, equals 0.2 meters. So it's good to convert to meters already. And there's no friction, right? It's just that it's got mass and can be treated as a uniform disk, meaning that the moment of inertia will be mr squared over 2. When the heavier mass has fallen for 50 centimeters, so 0.5 meters, what's the linear speed in meters per second? So not omega, we're trying to look for v. We're trying to look for v final. So what's the linear speed? Okay, so let's see what we could do. All right, so excuse me. Let's see. Let's draw a free body diagram for each of these objects. Okay. So it's a good thing that we have enough space here. Okay. So let's draw a free body diagram for the big mass, right? The 2 kilogram mass. Okay. So for big mass, we have tension going up, and we're going to call it tension 1, right? In this case, the tensions will not be the same because now we have a pulley with mass, right? Meaning that we're going to have an angular acceleration over there. Now we got tension going up and we got big mg going down. Now for the second mass, we got little mg going down and we got tension 2. Let's call it tension 2. Okay, so we have something like this. This is tension 1. This is tension 2. Okay, tension 2 going up in this case for little m. Now, let's do a free body diagram for the pulley. Now for the pulley we have mg, right? So m of pulley, mp times g going down, and well, the normal force, Fn. But let's also do a free body diagram for the sum of the torques. So how would we do this? Well, it just goes like this. There's the pulley, right? And then there's one force going this way, which is T1, and one force going this way. And we know that the acceleration will be in this. The angular acceleration will be like that, meaning that T1 will be positive and T2 will be negative. Okay, depending on the sum of the torques. Now, let's use Newton's second law. The sum of the forces equals to the mass times acceleration to describe all of these free body diagrams in equations. So let's do it over here. So the sum of the forces, okay, for the big mass, right, will be equal to big mg, okay, minus T1, which equals to big M times the linear acceleration, which we don't know just yet, right? Okay. Now, the sum of the forces for the little mass, m, so it's going to be, in this case, because we're moving, okay, because the tension is moving in the positive direction, then tension is going to be positive. So T2 minus little mg equals to little m times the linear acceleration, ma. Okay, and the third one, well, the sum of the forces for the pulley will be, that's just going to be Fn, right, minus mpg equals to 0. So that's kind of irrelevant, right? So Fn equals mpg. We don't really need that information, but that's just there. And finally, the sum of the torques, right, equals to the force times the force cross the radius, right, r cross f. In this case, we have two forces. We have T1 and T2. T1 is in the positive direction of rotation, so we have T1 times the radius, and then minus T2 times the radius. All of that equals to I alpha. Okay. We can already kind of simplify this equation over here by substituting the moment of inertia that we know from the disk, right? And by using the definition for angular acceleration, right? In terms of linear acceleration. So we know that T1 times R minus T2 times R, okay, equals to mr squared divided by 2 multiplied by, right, the acceleration, linear acceleration, divided by the radius. So look at that. This one cancels out. We're left with 1r on each term, which means that all r's cancel out. So we know that T1 minus T2 equals to m times linear acceleration divided by 2. And we can use this equation, okay, with other equations. So in this case, as you can see, T2 is negative over here and T2 is positive over here. So if we add these two equations, okay, if we add those two equations, T1 minus T2 equals to ma over 2 plus, okay, T2 and then minus mg equals to little m times linear acceleration. The T2 is cancelled, and we're left with T1 minus little mg equals to 1/2 ma, big Ma, right? So m, big M over 2 plus little m multiplied by a. And so we would have found the acceleration, but of course, we don't know what's t1, right? So we have to solve for t1 in some way. So we know from this first equation that t1, okay, t1, let's write it over here, t1 equals to basically mg minus ma, right? So we have big M, g minus big Ma, right? That's going to be T1 minus little mg equals to big M over 2 plus little m multiplied by the acceleration, the linear acceleration. So now we can find the acceleration of the system. So the acceleration will be equal to, okay, look at that. We can factor out some things in here. Well, actually, we'll have to move this to the other side, right? So we'll have m, this m, right, plus this m over 2 plus this m. Okay? Now, oh, remember, by the way, that this m that we're talking about over here on the sum of the torques is the mass of the pulley, right? So let me clarify that for a second. That's the mass of the pulley. Okay, this m over 2 is the mass of the pulley. Okay, very important. Now, we're going to have something like this. We're going to have big mass minus little mass multiplied by gravity, right, times g. All of that divided by mass of the pulley divided by 2 plus little mass plus big mass. Okay, and that's essentially the acceleration. Okay, so once we find the acceleration with the given values, let's see. Well, that's going to be, okay, we know that the big mass is going to be 2 kilograms, right? So it's 2 minus 1 kilogram, which is the smaller mass, times 9.8. All of that divided by the mass of the pulley, which is 4. 4 over 2 is 2, plus little mass 1, plus big mass 2. That's all going to be a total of 5. And the acceleration is found to be 1.96. Of course, meters per second squared. Now that we find the acceleration and we know it's constant, right? We can use one of the kinematics equations to find the linear speed once it's fallen 0.5 meters, right? So we have a distance, we have displacement, right? We have delta y. We also have the acceleration that we just found, which is 1.96 meters per second squared. We have the final velocity, right? I mean, common sense, right? V final has to be 0. Oh, I'm sorry, no, it can't be, right? Because that's what we're trying to find. But we do know V0. V0 is just 0. That's the one I'm talking about. That's 0. Okay? Meters per second. So we have velocity, we have acceleration and displacement. It sounds like the third kinematics equation, right? Because we don't have time and we don't want to bother with it. So V final squared equals to V0 squared plus 2 times the acceleration times the displacement. So we can solve for the final velocity, and we have that's the square root of 2a delta y, given that V0 is 0. We substitute our values, and V equals the square root of 2 times the acceleration, which is 1.96, times the displacement, which is 0.5. And so the velocity is 1.4 meters per second. Okay, so that's your answer. That's the linear velocity. Okay. Here's the formula sheet. Yeah, you might need it. Well, thanks for watching. I hope you found this video useful. I wish you the best of luck for tomorrow's test. And make sure to double check your answers if you have some time left. You know, if you get stuck in a question, just move on, come back to it later, you know, try to remember all these equations, because usually just like referring to the formula sheet for every question is not a good idea. So try to familiarize yourself with the equations and the meaning that they hold, right? So you can do well on this test. I'm sure you'll do fine. It's not an extremely hard test. So I'll see you next time. Thank you.